Good morning. We developed the formula for the minimal polynomial over GFQ of an element beta in the extension field GFQ to the m. The formula used the notion of the conjugates of beta with respect to GFQ. In this lecture, we'll use this theory to study the factorization of x to the n-1 over GFQ.
The goal of this lecture is to describe the factorization of x to the n-1 over GFQ. By describe, I mean that we'll determine how many irreducible factors x to the n-1 has over GFQ, the degrees of these irreducible factors, and also the roots of these irreducible factors. This is relevant to this chapter because we saw in Chapter 5 that the canonical generator for a cyclic code of length n over GFQ is a monic divisor of x to the n-1. And so by learning about the factorization of x to the n-1, we'll see how canonical generators g of x can be selected so that we have a useful lower bound on the distance of the cyclic code generated by g of x. We'll call these codes BCH codes. Let P be the characteristic of GFQ. So Q is some power of P. Suppose that Q and N are not coprime. This means that P must divide N since P is the only prime factor of Q. Then I can factor out P from N at least once, let's say a total of L times, leaving a cofactor N bar, which is coprime with Q. And then, by the Frosch's dream, I can partially factor x to the n-1 as xn bar minus 1 to the power p to the l. I can do this because p to the l is a power of the characteristic of the field GFQ. And so, factoring x to the n-1 over GFQ has been reduced to the problem of factoring xn bar minus 1 over GFQ, where now n bar and q are coprime. So without loss of generality, we'll assume in the remainder of this lecture that n and q are coprime. Here's some notation I'll use in the remainder of this chapter. Let m be the smallest positive integer such that q to the m is congruent to 1 modulo n. In other words, n divides q to the m minus 1. I'll state as a fact, which I won't prove, that such an m exists. We'll let alpha be a generator of the multiplicative group of GFQ to the m. And we'll define beta to be the element alpha to the power q minus 1 divided by n. Note that beta is an element of GFQ to the m since alpha is in GFQ to the m. Let me argue that the order of beta is n. This is because beta is defined to be alpha to the power q to the m minus 1 divided by n. Since alpha is a generator of GFQ to the m star, the order of alpha is q to the m minus 1. And so the smallest positive power of beta, which gives you 1, is the nth power. Now, since the order of beta is n, the elements 1, beta, beta squared, up to beta to the n minus 1 are distinct. Furthermore, each of these elements beta I, when raised to the power n, can be written as beta n to the power I, which is 1 to the I since beta to the n equals 1. So each of these n powers of beta are nth roots of unity. And this means that these n powers of beta are all roots of the polynomial x to the n minus 1. Since this degree n polynomial can't have more than n roots over any field, the complete factorization of x to the n minus 1 is given by this product of linear factors x minus 1 times x minus beta times x minus beta to the n minus 1. But this is not the factorization that we seek, because the coefficients of these linear factors, for example beta and beta squared, are in GFQ to the m, not necessarily in GFQ. And so this is the complete factorization of x to the n minus 1 over GFQ to the m. But this may not be a factorization over GFQ. As it turns out, some of these linear factors of x to the n minus 1 can be grouped together, so that when they're multiplied out, the coefficients are indeed in GFQ. We'll see how the linear factors can be grouped together in such a way that we recover all the irreducible factors of x to the n minus 1 over GFQ. And thus we'll obtain the complete factorization of x to the n minus 1 over GFQ. So let's consider one of these powers of beta. I've chosen the ith power, where I is between 0 and n minus 1. Since beta to the I is a root of x to the n minus 1, we know that its minimal polynomial over GFQ is a divisor of x to the n minus 1. Recall that this minimal polynomial is an irreducible polynomial over GFQ. Furthermore, the roots of this minimal polynomial are the conjugates of beta to the I with respect to GFQ. And these conjugates are beta to the I, beta to the IQ, beta to the IQ squared, up to beta to the I times q to the t minus 1, where t is the smallest positive integer such that the next conjugate in this list, namely beta to the power I times q to the power t, equals the first conjugate beta to the I. Now, since beta has order n, this condition on t is equivalent to saying that t is the smallest positive integer such that I times q to the t is congruent to I modulo n. I'll next introduce some notation for the exponents of beta in the set of conjugates of beta to the I. Suppose that q and n are coprime, and let I be an integer between 0 and n minus 1. The cyclotomic coset of q modulo n containing I is the set Ci, which contains the number I, and the numbers you get by repeatedly multiplying I by q modulo n. So we have I times q mod n, IQ squared mod n, and so on up to I times q to the t minus 1 mod n, where t is the smallest positive integer such that I times q to the t is congruent to I modulo n. In other words, the next element in this list would be I times q to the t modulo n, which is equal to the first element of the list, namely I. Also by C, I'll denote the set of all cyclotomic cosets of q modulo n. So this is the set of all cyclotomic cosets Ci as I ranges from 0 to n minus 1. Here's an example. Let's find the cyclotomic cosets of 2 modulo 15. So here q is 2 and n is 15. And note that 2 and 15 are coprime. So we first have C0, which is comprised just of the number 0. Next we have the cyclotomic coset containing 1, C1. This has the number 1 in it, q times 1, which is 2, q times 2, which is 4, q times 4, which is 8, and then q times 8, which is 16, which is the same as 1 modulo 15. So C1 has size 4. We'll note that C2 equals C1, and that's because C2 is comprised of 2, 4, 8, 16, which is 1, and then 2 again. Similarly, C4 equals C1, and C8 equals C1. Next, we see that C3 is comprised of 3, 6, 12, and 9, and that C6, C12, and C9 are all equal to C3. C5 has 2 elements, namely 5 and 10, and C5 equals C10. And finally, C7 has size 4. It's comprised of 7, 14, 13, and 11, and C7 equals C14, C13, and C11. So we've considered the cyclotomic cosets of all the 50 numbers between 0 and 14. And we've obtained 5 distinct cosets, C0, C1, C3, C5, and C7. So the set C of all cyclotomic cosets of 2 modulo 15 has size 5. Observe that these 5 distinct cyclotomic cosets of 2 modulo 15 partition the set of all integers between 0 and 14. This example suggests that if J is an element of the cyclotomic coset containing I, then Cj equals Ci. This statement is easy to prove. Recall that the roots of the minimal polynomial of beta to the I over GFQ are precisely the conjugates of beta to the I, and that this minimal polynomial is an irreducible factor of x to the n-1 over GFQ. We also saw that we can write this polynomial in fully factored form as a product of linear factors, where the roots of the linear factors are the conjugates of beta to the I. So we can write this factorization more compactly as a product of all linear factors x minus beta to the j, as j ranges over all elements in the cyclotomic coset of q modulo n containing I. And that's because Ci is comprised of the powers of beta that you see in this factorization. And so the minimal polynomial of beta to the I has a degree equal to the size of the cyclotomic coset Ci. Recall also that the distinct cyclotomic cosets of q modulo n partition the numbers between 0 and n-1. And so, as Ci ranges over all distinct cyclotomic cosets of q modulo n, the minimal polynomials of beta to the I range over all monic irreducible factors of x to the n-1 over GFQ. This establishes the main theorem of this lecture. Suppose that n and q are coprime. Then, the number of monic irreducible factors of x to the n-1 over GFQ is equal to the number of distinct cyclotomic cosets of q modulo n. Furthermore, the number of monic irreducible factors of degree d is equal to the number of distinct cyclotomic cosets of q modulo n that have size d. We'll see 2 examples of this theorem in the next video lecture. We've done all the work now in understanding the factorization pattern of x to the n-1 over GFQ. The next lecture will present 2 examples of this theory. Have a great day.